Now, let's look at the one example on how to find the absolute value of some complex number. Now, let's look at the page 622, and we look at the problem 4. So we need to find the absolute value of this complex number and graph this complex number on the complex plane. So let's go back to the whiteboard. So this is the page 622, problem 4. We have such a complex number, actually is a real number, right? So the absolute value of this complex number by this formula, this is equal to the square root of the square of -6 plus 0 square. How do we get a 0? Actually, you may rewrite this negative root of 6 as the negative root of 6 plus 0i. So the imaginary part of this complex number is equal to 0. And this is why we got a b. This part equal to 0. So now this is just equal to the square root of the square of the negative root of 6. We know by the property for the square root, this guy is equal to the positive 6, right? Actually, when we talk about the real number, this is same as the absolute value of the negative root of 6. So in this case, the absolute value of a complex number is same as the absolute value of a real number. Now let's look at another one. Now let's look at the problem 12. -4 minus 4i. So -4 minus 4i. So first, let's get AB. A is equal to -4, and B, the imaginary part, is also equal to -4. So now the modulus R is equal to square root of A square plus B square, and this is equal to the square root of the square of -4 plus square of -4. So this is just equal to 4 square times 2, right? You have the 2 4 square, and then you take this square out, so you have the 4 times root of 2. So this is the modulus of this vector. Now let's do a short review about the basic operations on the complex numbers. And it's quite easy to add or subtract the two complex numbers. So you have the a plus bi plus c plus di. You add the two complex numbers. You just need to add the real parts and the imaginary parts. So you have the a plus c, and then plus b plus d times I, right? But it's kind of complicated and difficult to multiply two complex numbers, and even more difficult to divide two complex numbers. For example, if we want to divide 1 plus 2i by 3 minus 4i, we need to multiply both the denominator and the numerator by the conjugate of this denominator, right? You need to multiply both this numerator by 3 plus 4i and this denominator by this 3 plus 4i. And then you convert the denominator into a real number. So it's kind of complicated. So now, after we have learned the trigonometry, we try to rewrite a complex number in the trigonometric form. So now let's talk about the trigonometric form of a complex number. And let's move to the next page. So let's first draw one complex number in a complex plane. So actually you can see a complex plane is just same as a rectangular plane, right? So you have 1 point AB, and this is same as complex number A plus BI. Then this is the modulus of this complex number. Then the angle formed by the line going through this complex number and the positive x-axis is called the argument of this complex number. So right now, this R is the modulus, and the theta is the argument. And you can see as in the case of the trigonometry, in the case of the vectors, this argument is similar to the direction angle, right? So theta is greater than or equal to 0 and less than 360 degrees. Okay. But actually, you can take the other angle. If you add the multiple of 2 pi or the multiple of the 360 degrees to an angle, you can get another argument. So the argument is not unique. Okay, let's look at the problem 14 on the page 622. And we need to rewrite this complex number in the trigonometric form and using the degree measure for the argument. So this is the page 622, problem 14, and first we have the -7. So now, in this number, actually this is a real number, we have the A, the real part is equal to -7. And the imaginary part, B, is equal to 0. So the modulus R is just, okay, the absolute value of this -7 is equal to 7, right? So now, let's first get the cosine theta. Cosine theta is equal to A over R. So this is equal to -7 over 7 and is equal to -1. And between the 0 degree and the 360 degrees, we know theta should be equal to 180 degrees, right? And then in this way, we can rewrite this complex number in this track form. Okay, just I forgot to tell you the track form for this complex number. Okay, let's do this in the general case. So here we have this AB as the coordinates of the point for this complex number, and then in this right triangle you have the A equal to R times cosine theta, and B equal to R times sine theta, right? In this right triangle, this guy is the B and this guy is the A. So you can rewrite this A and B in terms of this R and the theta. So now this A plus BI is just equal to R times cosine theta plus I times B times sine theta. And then hold on. This should be the R times theta, not a B. Okay. So I times R times sine theta, because this is the I times B. So B is equal to R times sine theta. And then we factor out this R. So we have R times cosine theta plus I times sine theta. And this one is called the trigonometric form of this complex number. So this guy, this is the trig form.